Okay, welcome everybody for this new Learning Monday series. Mondays is all about you to learn. We tend to do hands-on. We have external speakers. Speaking of which, today it's my pleasure to introduce Vesa. Hi.
Hello.
So he will talk us about Kubernetes, building Kubernetes native apps. Because now when you build apps, you really have to be focused on, okay, how should I build my application, the Kubernetes deployment? It's not that easy, all the resources that Kubernetes should handle and how to provide parameters and everything. He will explain you all that today. But maybe can you please introduce yourself?
Hello everyone again. My name is Sevolot, but the short one is Seva. That's how I'm known to my English-speaking colleagues. I'm working for over 10 years in IT field, and we started with Kubernetes quite a while ago. And since that, I lost a couple kilos and sweated a lot. And today I'm gonna share some stuff that I encountered during my professional career with you guys.
Okay, so for this session, I will Seva deliver the content. I will read all your questions, note the question, and I will go back in the end of the presentation asking all the questions just to have fun. Okay? And from now, I will simply disappear like that and let you the floor. So
thank you, Cedric.
3,
Okay,
2, 1.
Let's start. We're gonna talk today about building cloud-compatible applications. Of course, this is very huge buzzword, but not really everyone understand what it means. I think I do, so I will try to share my experience with you today, and let's see what this will be about. We're gonna go, let's say, in historical way. So we're gonna observe how internet and application development look back in the days, and how demands to web development, as we are in web development field, are growing, and how do developers are coming to solve these new challenges. So today we're gonna take a look not only at development, but also we'll take a huge deal of our attention span to infrastructure layer, because that's quite important, and that's where everything like Kubernetes compatible application is growing from. And let's go ahead and take a look. There's some info about me, which I guess not that relevant for you. Just take a brief peek, and I already told something about myself, so I won't be delivering much more words in here. Okay, let's go to the fun part. So before, let's say in around 2000, developers were mostly building single application based on some huge framework like JBoss, or something like Symfony framework if we're talking about PHP, or some framework that allowed you to deliver stuff that user sees, as well as the stuff that runs the business logic on the background. I won't be delving that much into structure of monolithic applications. Probably if you're working in IT field, you met a lot of them. Almost every application that's written 10 years ago or 15 years ago is a monolithic application. That's no doubt. And what does it mean for us is all the logic are stored within the same project, within the same place, probably split by modules if you're a good developer, probably not if you're a bad developer, but still it contains somehow within the single project. And usually this project has one connection to some external service, something like database or some more specific service. If you're doing, for example, we were doing some telephone calling, so we had a connection with ATA, but doesn't matter. So this is mostly a single application packed into a single piece of code, running everything starting from what user sees to what backend developer sees in the background. So these old ways required some not special, but they required some infrastructure, because your code cannot just run in vacuum. So that required an old infrastructure that requires some infrastructure setup. So you had a physical machine with Unix-based OS. Usually that's Unix-based because Unix is much more flexible than Windows, but you also had the Windows servers. That's just my personal preferences, so sorry for making you biased, guys. It had some replicated disks because RAID techniques are quite well known. You set up 2 disks for, let's say, 100 gigabytes, and one disk is storing data, and another disk is just a backup. So you're working with that as a single disk, but they are being replicated. So if one disk is going away, another is taking over, and all these metal, all these devices were running your single application code container. For Java, it's a jar container. For PHP, it's a PHP container with it's PHP code with some interpreter. Doesn't matter. So that was delivered highly manually by uploading files via FTP, SSH, or some transfer channels, or even in the worst case scenario, we had some special trained guy who was just picking up the physical data drive and inserting that into some USB hub on the data center. And of course, this was backed up by a web server. Not necessarily, because you could have it also built into the physical machine, and it was running traffic through. In some cases, you could have a database split to separate machines just to increase redundancy. So if you have, let's say, fire in your data center, you could at least copy that and do not lose all the data on the single machine and making your business at risk. And they were usually connected by network, meaning that it was just a physical cable between 2 machines with some IP addressing and routing. So nothing special. You can assemble such stuff at your home easily, just connecting 2 computers to each other. Yeah, that's very old way. That's the most obvious way of delivering software. That's how developers and administrators deliver that in the past. But also, we should take a look what internet was in the past. That was quite a lonely place, I would say. So according to the data from Internet Database, in December 1997, which is 23 years ago, there were just 7 million people connected to the internet all over the world, mostly in North America, but also fraction here, fraction there in all other countries. And these people... You can imagine, right? You have an Earth globe with 6 billion or 7 billion people at that time, and you had just 70 million people in the internet, which is not that much. And also, these people in the internet are not that widely presented as of now. They just presented with the speed of 56 kilobits per second. For those who didn't use modems back in the days, who was so happy to be born at 2000 or later, I will explain. So you had telephone, you had the landline, you had some special device that was connecting to the landline and sending some highly analog signals encoded, and due to natural limitation of this landline, it was very, very slow. So it was like you could have a page with a text that just been loaded over 5 minutes, also multiplied by the fact that your computer is quite slow. And also, in case someone wanted to call, they couldn't, because they picked up the phone and they heard some weird satanic sounds directly from hell. So also, according to Cisco measurements, there was just 150 terabytes traffic flowing internet per month, and I mean that's not that much. We are having hard drives and data centers that are bigger than that nowadays. And also, of course, you didn't have that advanced technologies, and websites were very, very lightweight, and users also were not that demanding. They didn't require a high speed on the internet because and high speed for websites loading, because basically you had a computer which had the problems with just moving your mouse cursor. And also, they didn't know what is a good internet service is, because back in the days you didn't have Amazon, you didn't have Google, you just had a lot of enthusiasts, homepages of some sort, like hello, this is my homepage, I love flowers, I want to share that with all the worlds, and then 2 photos of flowers that were loading for ages because they were 1 megabyte god damn it, huge, and they couldn't be loaded at the time. And also there were no smartphones, right? So users just had a huge stationary computers, at the best laptops. Only very rich people could afford those. So there were not really that much people in the internet spending that much time in the internet. Yeah, so I mentioned that no Amazon, no Google. Of course, Craigslist was there. Craigslist was always. And nowadays, internet is much more crowded place. So there are 5 billion users in the internet in 2020, meaning that more than half of the Earth population is spending some time in the internet, or most of us are spending a lot of time in the internet. Also, with a higher speed because of the broadband connection. Broadband connection is widely spread all over the world, not only in the first world countries, but everywhere. Also, Elon Musk wants to run his satellite network, which would provide us huge channels everywhere, including some Everest mountains and stuff. Also, you're using your smartphones a lot, and smartphones are doing a great deal because now you don't need to go to the computer to go to some dedicated place. You can just take a look at your smartphone. And of course, we are having Amazon and Google. We are having some really, really advanced services that are really advanced and providing services to users. And users are got used to this really outstanding quality of service. And moreover, websites should do some heavy calculations. If you want to stay in the business, if you want to analyze, if you want to make sales, you should be able to deliver metrics. You should be able to deliver marketing data. And there are a lot of tools for that, and a lot of tools that require computational power and require some certain approaches to that. Also, we have fast computers. User now demand a high speed because user can click every icon on their computer, it will work right away, and they demand the same from the websites because for the average user it doesn't make any sense to divide them in his mind. So that led us to new challenges for software devs. Now we should know that 5 billion people in the internet, right? In a worst case scenario, 0.0001% would require your services, and still this is a lot. This is like 10,000 people, 20,000 people, but they won't know about you in the single minute. So what you have to do is you have to build up a tiny little system that would deliver just the main functionality and then be able to really, really grow up fast, because the advertisement that is being provided through the internet can acquire new users in no time. Let's say Facebook advertisement can have 1% of conversion per 10 million impressions. That meaning that 100 users will come to your page every second, and you need to be able to react to that. Also, you should be able to adapt. Let's say your website was crafted with or your web service was crafted with some thoughts in mind that you figured out later are not correct, and then what you do, you should be able to instantly switch it, instantly deliver the new version of website. No more guys running with the physical data storage between data centers. That won't work anymore. And businesses also have changed. They now need to test new hypotheses. And if before testing new hypotheses meant that you should do a new release, print out CDs or print out floppy drives, even if we're talking about 95, but now people are just like, we need to deliver this feature next week and deploy it everywhere, and people should get access to that instantly. Also, when devs are picking up some technology, some database drivers, some network drivers, they also should be able to really be able to switch them in case they will figure out that this is not the way to go. And of course, for developers, business makes hard and strict requirements to deliver code really, really fast. Before 2000, delivering code really fast meant you could develop and deploy a feature in 2 months because you had some time. And now it means that you have to deliver features every week, or in the worst case scenario, every day. And with all of that mentioned, you should still be able to be secure, because hackers, script kiddies, their amounts are also increasing. We had some very romantic movies that led people to think that they can hack everything. So yes, let's continue and take a look to the approaches that were picked up on both application level and deployment level. So I will start with the server's infrastructure, and I will take a look at what do service infrastructure per se would provide. It's very important for you as a developer to know that as well, because your responsibility is now not only writing code, but we will talk about that in a few. So we had a virtual machines, we had virtual machine service meshes, we have still bare metal servers. I would talk about that a bit later. And we had configuration management tools and containers that allow sysops or DevOps or system administrators to deploy your code faster. And also it allows you to have some flexibility that you also should know about. And of course, for developers, the huge step forward, the huge leap, I would say, is continuous integration and deployment systems. Let's start with virtual machines. What virtual machine is. So back in the days in 72, one smart guy figured out that your computer is like not in 72, of course, but he thought that your computer can be so powerful that it can act as 2 or 3 different computers with different virtual systems, with different OS, with different layers of hard drives. And that's where first virtual machine kicked off as a software concept. Before that, it was purely software. In 2006, Intel provided hypervisor technique, integrated on the hardware level, which of course always faster. So virtual machines really started rising in 2006. So what it basically is you can create multiple machines with different operating systems on the single machine called host machine. And also you have some certain layer called hypervisor, which manages all the resources. So technically you can create one weak machine, one medium machine with different resources. Let's say you have 2 gigabytes of RAM, you can create one machine with 500 megabytes of RAM and one with 1 gigabyte of RAM, depending on your tasks. And also they would be completely isolated unless you would do some special procedures. You cannot access host machine from virtual machine. And of course, you could definitely guess where I'm leading to. So this approach became very popular amongst hosting providers, because you're not risking your bare metal server, your physical server anymore. You're just creating a virtual machine. This virtual machine is isolated, it's secure, it allows you to flexibly control the resources, and you can provide this to your customers. So your customer requires some small little a server, and you don't need to buy this small tiny server. You can just create a tiny virtual machine on your huge powerful server, and that would act as it. And that's how a virtual machine came to hosting providers in a really fast pace. I think it started in 2006. In 2007 I could already buy a dedicated server based on virtual machine. So how hosting providers are organizing that is via service meshes. So it's very convenient mechanism. You have a virtual machine, you have a set of virtual machines, you have a special machine or software standing in front of them, because virtual machines can also be spread over multiple hardware pieces, right? And that where it controls which user has access where and which user can do what on its virtual machine, and how do we route customers for these users to some certain machines. Basically, you can consider that as just a plain firewall. If you don't know what firewall is, it's just a tool that limits some certain connections to somewhere. Like you cannot connect to port 80 on your computer, but you can connect to port 53 because this is where your FTP server is running, or vice versa. Or you have your God forgive me, you have your Counter-Strike server somewhere, so you open this port and your internal firewall is blocking every other connection, disallowing any people who can hack you or penetrate your system to not to do that. So that's how service meshes appeared. And then let's talk about dedicated bare metal service from hosting providers, because they didn't go anywhere. So as I said before, all servers used to be bare metal service in the past. So that's basically the tiniest unit of server infrastructure that you can have. So it's always a single tenant, because it's basically just a machine with OS installed, and that's just that's just a machine like your home PC or any server you're working with, but this is just hosted on the server. So that's the most plain connection to the hardware, meaning that of course it's not it's cumbersome and tedious for a system to host everything as it does with virtual machines, and therefore you're dropping a hardware costs. But on the other hand, you're increasing administrative costs, because if your virtual machine acts weirdly, you can just restart it and it will raise up in no time. But with the bare metal service, you should physically restart the machine, probably involving some special trained guy who would just flip on the switch and flip it back again. But yes, it's still valid. A lot of companies are using that, especially big companies, because it's the most computational power of every approach possible. And you can also use it for some special tasks like mining bitcoins or serving some special databases with, let's say, special computations, because it can have some special hardware, because virtual machines are not that good. They're just a common hardware machine, so they cannot handle this special hardware. And of course, people in the data centers are not doing that by hand. Let's imagine you have 1,000 web servers, you have 10,000 of virtual machines, you have everything. So, and if you would just have a system administrator, which you would just type in commands for each machine, that would be quite counterproductive. Like you got 10,000 servers, you should set them up in a rack, which is not actually that tedious, but then setting it up one by one would take human years, and also salaries of some good paid specialists. That's how configuration management tools were invented. They are just uploading the configuration files, which is basically just a plain file enumerating the commands that you should run. And that's how you can set up 10,000 servers at the same time. If you have some system administrator amongst us, or some former system administrator, they will probably have a smile now, because they definitely know what is this all about. And we are, as a developers, not that interested. It's just, for me, is a good bridge to come over to what follows next. So Docker and Kubernetes, a big buzzword since it was released in 2010 from Google by the name Borg, which I definitely like more than Docker, because that's a Star Trek reference. Never mind. So that's not so a lot of people think about Docker containers as some sort of virtual machine, which is just more fancy. It's not. So what is it? Is you have a system, you have a thin layer of isolated libraries, and these isolated libraries are communicated with this machine hardware directly. And also, Docker was built perfectly only for isolating virtual machines, for isolating machine environment from each other on a software level. So that's more like a very programmatic tool to be able to be secure, and also it has some features that we'll talk about in a few. So we have on this channel, my colleagues from DataStax are having an amazing presentation of what Docker is and how to learn Docker, and I would highly recommend to each developer to delve into that. It's not that hard, it's not that complex, but it will moderately increase your cost on the market, and also your knowledge, and of course your fanciness as a developer, because if you have this hashtag, you are two heads ahead of every other developer. So let's talk about Kubernetes, because this is the next step to Docker. After Docker was released, that wasn't that much. So it's just an isolated container. The concept is as simple as that. But what happens if you need to build some mesh of services? Like, let's say you have a database which is separate. You have one of your application which, let's say, sending emails. You have another application which connects to database, fetches some data, processes that, and sends email if necessary. How do we connect them? How do we test them? We have Docker, which allows us to separate our environment, and which also allows us to emulate the same environment we have on production services. But how do we connect this to a network? How can we test this? How can we have a very convenient way of scaling multiple Docker containers? So Kubernetes gives answers to all of that. So this is a tool that is basically just a Docker container manager. So what it does, it controls the Docker containers. It gives them some commands like run, stop, restart, die, be deleted, and so on and so forth, and has some nice API that allows developers to also control the Kubernetes itself, and of course these Docker containers inside the Kubernetes. And also, what Kubernetes is the tool that allows you to build a network of your hardware and unite this into one Kubernetes fleet that you can control as you were on the single machine, which is very cool feature and widely used by the hosting providers and these so-called cloud services. So basically, when you hear about cloud service, that's basically Kubernetes. It will be there by some other name maybe, but that's basically it. And also Kubernetes, along with Docker, brought the concept known as a horizontal scaling. So basically you have two types. So vertical scaling is something when you're just adding resources to a single application, which is good for monolithic applications, but resources are end. And the resources has an end. And for that you should, and considering that, you should know that you cannot grow endlessly, and you should at some point think about how people can be split between the multiple instances of the same applications, because you can't buy more machines, you cannot buy faster CPUs at some point. So, and Kubernetes gives you incredibly easy answers to that. You just buy a new machine, new server, you set it up with tools I enumerated previously, and with these tools, and then you just add this to Kubernetes and say Kubernetes scale up more, and Kubernetes would just use this machine. So this led us to modern approaches. So as I mentioned, developers are now able to control Kubernetes API. So this is an even bigger extension to infrastructure as a code, meaning that you don't need to run to your data center anymore or do some physical stuff with it. You just run a set of commands sitting at your convenient office chair or your convenient rocking chair if you're at home, and then you were just able to control everything. And of course, along with that, Kubernetes defined rules for writing efficient applications, because it's not that easy. And of course, you as a developer, it's your responsibility to know that in case you're working with a cloud infrastructure. So let's take a look at that. So how do we build in Kubernetes native apps? That's where our story of sweat and tears is kicking off. It has some logical parts that I try to split as much as possible, but I would say inevitably mix them up. So sorry for that, guys, in advance. If you feel insecure or you don't understand everything, just wait a bit, or just don't hesitate to ask questions in the chat. So Cedric is there and he will be happy to answer them. So let's start with the development preparation. What is development preparation? That's maybe not the best term, but this just means that developer is responsible now for preparing a Docker image. SysOps and DevOps is a new thing, is a new branch in infrastructure, and is a new profession which requires a lot of skill. But basically, the task of preparing a very basic Docker file so your application will run in the environment that it needs. So with all the libraries and all the DLLs, if you're running on Windows, installed if needed, it's only your task. So you should be able to know how to write Docker file. You should know a little bit how Docker works. Internally, you should test it locally, because running Docker locally is very easy on each system, including Windows. And so, and you have all the power and all the tools, and you have a lot of material on the internet, but preparing Docker file is not easy, because I never met a developer who just started with Docker files, who doesn't have an experience with the clouds, and who could prepare a decent Docker file from the get-go. So it doesn't work this way. Usually these Docker files are huge and cumbersome and hard to read. So you should definitely get a finger on that and make some muscle memory even to be able to write them. So also that means that deployment pipeline increases because deployment pipeline complexity increases, because before developers were just producing code without thinking about Docker and Kubernetes and all that bullshit, and there was just a guy who was deploying this to production service with an FTP build, and there was not that much to think about. And now we have very high standards of ivory tower development. Like, developers are doing code, developers are creating merge requests, and then team leads or reviewers are approving these merge requests, leading to containers being built. Then you have a Helm chart, which is a tool for generating Kubernetes deployments, and then it generates Kubernetes deployments and goes to Kubernetes, and also Kubernetes does some magic inside. So for developer, it's now insanely hard to track everything. And this is a theme for 6 separate presentations, but we're just about observing here. So just keep that in mind. If you're being hired to a company, or you want to be hired in a company that uses cloud infrastructure or Docker or Kubernetes, the pipeline would look like that. So let's switch to actually application itself. How do we write code for this application? So the first thing that is worth mentioning is application should be stateless. I would emphasize that none of these rules is carved in stone. So, I mean, when I'm saying that application should not be stateful, should be stateless, that means that in 99.9% it should be stateless, but you can have some certain approaches, some certain problems where this just doesn't work. So just keep that in mind. Okay, so let's go to stateless. So what does it mean? Application should never, ever store any session or return data inside the Docker container and moreover inside RAM. That comes from the fact that Docker containers are highly ephemeral, which means that Docker container can die at any moment. And in Kubernetes environment, it happens all the time. Like, let's say one of your servers in the network went down, virtual machine went down, or something happened, part of the network connection got lost, and then Kubernetes, what it will do, it will redistribute your deployed application to other services, but of course it will kill the application first. And if your application is saving some critical data within memory, it would lead to bad consequences, because it won't be stored anywhere, it won't be flushed to disk, it won't really be saved, because hard drives that because the thing that is treated as a hard drive inside the Docker containers is just some temporary storage that would be erased once Docker container is down. And you will ask me, like, yes, we won't be able to store any data in the container. How do we do that? So you establish a connection to something that called stateful layer or persistence layer, and store all the data that should be persistent in that stateful layer, like database. Or you can also, Kubernetes allows you to mount some hard drive, some physical or virtual hard drive, which will be more persistent, so you can store it in there. Something like images for your website and stuff, which should remain there for a while. And also, please keep in mind that user session also belongs to persistence. So it should not be stored in your machine, because let's say you can have multiple machines. You remember about horizontal scaling, right? You can have multiple instances of your website, and then your website will store user data on one machine, then user clicks somewhere and goes to another machine, and then session is not being stored in there, and then user feels like he's been logged out to this website. So that's a very, very bad pattern. Each of your application instance should communicate with database and not share data between each other. I'll emphasize again, this is not carved in stone. You probably encounter over your professional career patterns or situations or cases when should not be like that, but this is a general approach. This is the first approach you should think about. I will give you one short example on how we had our problems with our application. So we had our application that was counting analytics for user website visits. So it wasn't just counting. So it was it got user data. It looked for some matches. It was processing data. It was recombining the data, and then it was storing that to database. So when we just ran it, we of course considered that application cannot store stuff directly to database because database would be a bottleneck or should be scaled a lot. And that's how we came to conclusion that each application should store some certain visits, like 50, and then flush them to database. And that's how we decided to go with that. And on the next slide, I will show you what it led to. So that's basically what happened with our deployment. So 2 applications were counting visits. One counted 20, another counted 30, did some processing, and then Node, the Kubernetes restarted one of our applications, and another one continued counting and just counted 30 and flushed data to database, and database contained 30. Cool. We had some inconsistent data in the database, and then when marketing guys went there and compared our data with what our partners gave them, they said that this is bullshit. So this should be 50, not 30. And this is just a very bad example of anti-pattern in Kubernetes network. So we allowed our application to be stateful. We stored some data, we stored some internal data before flushing that to database, and that's where we failed. So you will ask me, of course, how can we organize that in a better way? And we will discuss that in a few. So let's continue to the next point in my presentation, which is scalability. So of course, I mentioned that already. As I said, I'm mixing these topics up because there is no particular order for that. And you should just, as a developer, keep in mind that you would have horizontal scaling. That's how Kubernetes was designed. That's what clouds are needed for. That's how modern software is working. And your application would not exist on its own. So you should actually think about what the consequences would be of application not existing alone in the universe. And the first thought that comes into my mind when I'm thinking about that is we should not design this in a singleton pattern. So your application should not act as if it's alone in the universe. It should not be greedy. It should not do any exclusive logs anywhere to be able to start, because that's a contradictory to what Kubernetes states. And also, it should not require any external service to be up before application starts up. So normally, if your application requires some external service and this service is not yet up, application should not just hold it. Application should say fail, I'm failing, I'm restarting. And then when external service would start, application at some point would just connect to that, and that's it. That's how Kubernetes is working. Failing is quite okay. Your application can be restarted 5 times before external service is available. That's also quite nice. So don't hesitate to kill your application on each requirement unsatisfied. That's much better than just holding something in the background and relying on a developer skills to be responsible for some checks on this application. And also, it may be a good idea to open idle connections to database, let's say, so you don't waste resources for reopening them, but it's generally a bad pattern because your application can be terminated and you will lose your open idle connections. And if you're not managing this properly, and this is quite hard with all the modern database systems, you would have dull connection on the database layer, and as we remember, this is not easily scalable. So I will give you an example about what have we done in our company. So we had 2 applications. It's the code is quite equal. I mean, not quite, it's equal. So this is just 2 different instances of application, 2 containers, 2 Docker containers running. So first of them, we decided that it would be quite good idea to log the database so we don't bring any inconsistencies during the startup, because application was done some job on the startup. So and what we had is the first application instances ran. It set the lock on the database. It started doing some some stuff in the background, like filling in the database, and then it crashed because it was restarted. We remember failing is okay. Then another application instance started, tried to acquire the log, could not because first application never released its log, and then we had no running application at all without any real problems behind. So that's what you should avoid, and that's how you should not write your applications, except for the very rare cases when you really need to set some logs just for data consistency. But for that, you should definitely know what you're doing. This application crash is highly possible. So let's take a look at responsibility split. What responsibility split is. So that's closely connected to another topic that you can meet everywhere in the internet. You can hear about it on all the development conferences. This is already a de facto standard in development. So this is microservices. Of course, microservices and everything that I said before about standalone applications and stuff is mostly about deploying microservices, because developing monolith are also able to live in Kubernetes environment, but all the Kubernetes and cloud services were designed for microservices. So it's very tempting to actually just start from microservices, because that would basically you will be doing on your daily basis on your job, or you're already doing that. But I do recommend to read about that a bit and think about that, because this concept is not very easy per se, as it seems. So there is a very good book from Sam Newman called Building Microservices. I mean, generally, most of O'Reilly books are very good, but this book I can definitely recommend to read. It gives you very nice introduction, very nice overview of what microservices is, and then on listening to all the conferences, you would be able to imagine what microservices are and what they represent. And let's go to responsibility split. So responsibility split is basically the concept lying in foundation of microservices. Your application should do just one job. So if you have your system which does user provisioning, which does user logging in, which does user doing a purchase, which does sending emails, which does, I don't know, delivering avatars or serving images, this is highly likely a monolithic application. And if you want to serve it in a Kubernetes, you should probably split it to email sending service, to image provisioning service, to user login services, and so on and so forth. So if you have within one instance multiple goals or multiple responsibilities, you can think about creating new containers with a specific function. Let's say if your application should run user logins and send emails, and you don't see any necessity of splitting this code, you can just split this to two Docker files, to Docker containers. One of them would be logging users, another one would be sending emails. And of course, the concept that Docker brings us as well is limiting resources. So you should not just rely on the server capabilities. You should never say that I need 4 CPUs and 3 gigahertz or 6 gigabytes of RAM for my function. That's highly likely not true, and you should think with which bare minimum resources your system can run, and with which bare minimum resources you can deliver everything. So this is also a hard topic. Let me know if you're interested in that. I have very good cases, and we can organize another Monday learning for that. So I'll give you an example. We had our applications doing migrations. So this was a responsibility. Application was doing some application job and was doing a migration to the database. And what we ended with is application was 3 instances of applications were trying to start migration. And even though a lot of migration systems are designed to exclude concurrency, it's not reliable, and it's quite hard topic for software development as well. So we had some inconsistency in the database, because a lot of applications were trying to apply the same migrations, and one applied it for 50%, another for 20%, and the last one could not apply anything at all. So it was not that good. It was very complex. And then at some point we came to the conclusion that it's much easier to just divide applications to applications that are doing applications job, and make a separate little container that just applies the migration. So just only one source of truth, no conjoinment, no intersection, nothing. That's basically what responsibility split is. If you think that your application does too many jobs, or these jobs are contradictory between application instances, you can also think about single application instance that will do your job, or multiple applications that will do your job in parallel. That's what I wanted to say about responsibility split, and let's move to startup and functioning section. So that's basically a very bad term for that. I didn't figure out anything better, but this is about how containers are being run inside the Kubernetes. So Kubernetes is a very complex tool, it's a very smart tool. What it does, it provides the necessary resources for Docker containers that are specified on a Kubernetes level. And so, of course, Kubernetes has requests and limits. And request is a bare minimum resources that Kubernetes should have somewhere free to run your machine. That's why I mentioned the bare minimum resources for this machine. And of course, limits is how much this machine can consume. So that comes from a concept that you can have one server with 10 Docker containers, and this server does not necessarily have the resources for all the containers working up to limits, but it can have some resources for containers that are temporarily running at limits and then going down again. Or it can actually kill one container and schedule it to another service which has more resources if this container is constantly at limits. And also, how Kubernetes understands that container should be dead, or how container is responsible for serving a traffic or making its main function. It has a readiness or liveness probe concept. I mean, not or, this is readiness and liveness probe existing in Kubernetes. So what readiness probe is, it shows Kubernetes that when your container is being able to satisfy this readiness probe, it is allowed to run traffic through this. So that's basically a signal for Kubernetes that your application is ready and it's ready to serve traffic, and it can run traffic through it, because Kubernetes is also responsible for a networking layer. We'll discuss that in a few as well. So it's your responsibility as a developer to define readiness probe. It can be some endpoint which Kubernetes just consume, and if your endpoint, let's say, returns okay, Kubernetes decided, yeah, it's okay. So if your application requires some database, it requires some service to be up and running, it should check everything in this readiness probe, and then when everything is satisfied and the application is up itself, it can send okay to this readiness probe. So this is an important topic that developers usually discussing with CISOs before starting any development. And liveness probe is much more simpler. So it just states to Kubernetes that this container is not dead and it should not be restarted. So container can be not ready for a while, but if Kubernetes sees that the container is not live, therefore not responding to liveness probe, it will restart it. So think about that as well. Maybe create another endpoint if you know that there is something in your code that can definitely go wrong and prevent users from having your services that rather better to be dead, right? You remember that. So just craft liveness probe as the maximum availability for your service. So craft it in a way that it will respond in like bad, everything wrong on each disturbance in the force. So also, the good advice that I'm giving as a senior developer or as a technical lead in my company is do not pay much attention to the language. So in each conference, you will definitely see this separation, like Golang is better than PHP, or Java is better than C, or something like that. So it's rather better to deliver your service in a language that you know than just hunting for features or some better Kubernetes compatibility from some other languages. So just pick up the language you know, just pick up the framework you know, or the framework that you've chosen, or the framework you want to know, and just start developing. So it's not definitely related to Kubernetes, but that's good to know. And of course, grab all possible metrics from your container. Like, your application is running, your application has some internal modules, and these modules can definitely have some numbers to measure. So please do not hesitate to put them into metrics. A lot of frameworks are already providing ready to use metrics. Like, let's say my favorite Spring Boot is a Java framework, is providing some metrics endpoint where it just says that this many threads are running, this many memories consumed now, and so on and so forth. So it's very nice to know, and it will help you later on. We will discuss that as well. So, and then you have to understand where bottleneck is. Most highly likely it would be a database, but please do not focus only on that. So just plan your bottlenecks accordingly and think about them before developing an application. Moreover, before creating a Kubernetes network. Let's take a look why I'm so focused on the bare minimum resources. Here is some examples of closest, not the closest, but one of the biggest Google clusters in Europe, in North Europe, so which is in Finland, and the pricing in there. So you see that that's actually pricing even for service that would never be restarted, because these preemptibles, meaning that Google will restart them from time to time, is quite low, right? Because this is just 2 cents for an hour. What can go wrong? But you should also understand that if you don't think about your resources, you easily consume 20 or 30 CPU months just serving services, just serving your applications to the customers, and then you are paying around $400 per month just for your applications to be run. So this is also a nice numbers for business that they should pay the bills about, and please do consider that. That's why I'm focusing on resources. Every developer should know what his application is capable of running on the bare minimum resources and what is capable of running on a huge pile of resources. There is not so many of good talks or presentations on that just comes with experience. So your older colleagues, your more senior colleagues would definitely help you with that. And we can also organize a short dev talk about that, where we'll try to clarify what's meant in there. So let's talk about persistence layer, which I mentioned a lot during my presentation. So the persistence layer is a database layer, basically, or any data storage layer. So what you should know about that: in most of the cases, except our beloved Cassandra, the databases are stateful. So that means the database is holding some state, and that's obviously what it's designed to do. And even cloud prepared databases are not easy to scale up or down. So these databases are hosted on 2 or 3 containers, because we have redundancy for high availability. It doesn't matter. So you cannot just say that, yes, my database is not holding up, I will just scale up new database horizontally, like you can do with your application. So applications can scale indefinitely, databases cannot. And when you're setting up a persistence layer within the Kubernetes, it would also mean that database would have also limitation on resources, and increasing this would definitely require a restart on database. That's why they kind of duplicated or even tripled over the network layer. So this is, in my opinion, which is not carved in stone, we can discuss about that in the comment section or on my LinkedIn page, is to be kept outside of Kubernetes, because this is where it contradicts most of the Kubernetes patterns. Kubernetes has some stateful patterns, but better to keep database outside of it. And if your responsibility as a developer to think would you connect to persistence layer, and how you would serve your traffic through. So also good advice to give about persistence layer, about databases, as if your team is small, and you really need some low maintenance solution, and you're ready to pay some money, and you don't have any DBA, you can think about vendor provided solution. A lot of cloud services, including Google, Microsoft Azure, and Amazon, are providing or ready to use databases, and you don't care about how they host it, or how they scale it, or how databases are being set, so how backups are being set. So you just use this database and you don't think about anything else. It's quite expensive, but for a starter, it's a good approach. And at the end, concluding everything that I said, and also returning back to an example that I've shown, let's talk about some architectural points. So you remember that I mentioned the application that was counting visits. So this analytics application where people were going in, and then some processing was happening on the multiple applications, and then everything was stored to database. So this is what we're calling event-driven systems. So something in the outer world is happening, and we're just reacting to that. That's actually and efficiently in nature of most of the businesses in the internet. Amazon reacts when you're clicking the page. Netflix reacts when you clicking play. Google reacts when you're typing something in a search string. So this is basically how things in the internet are being crafted. And on each event, you should act somehow, and probably you should act in a short time frame. And it's highly likely that you require some definite computations that are quite long, and that's where people invented publisher subscriber or pub sub architecture. So the good thing about publisher subscriber is that you have some special pieces of software or even hardware. I mentioned dedicated bare metal servers before, which allows you to split the responsibility. So your application, as the gateway to the user, is only responsible for forwarding clicks further. So just assembling, maybe doing some slight computation and forwarding it to something called queue. What queue system is the special software which designed, it's basically sort of database which designed in a way that you're pushing messages to that, and from the other side you can consume these messages, and it will keep track on which message was consumed, and of course it will store it for some time, and of course it's designed to have as high throughput as possible. So a couple of examples is RabbitMQ or Kafka. That's software solutions that you can use to organize a queue. There's a lot of them. You can just Google queue software and you'll definitely find something, because this is also a topic for a separate discussion and a separate presentation. And then on the other hand, on the other side of queue, you have one or multiple processors. So you see this horizontal scaling available on both sides, which does all the heavy computations and stores the stuff into database. That's how most of the publisher and subscriber systems are organized. You don't need to do immediate heavy computation and makes user wait. You can just do bare minimum that's needed to a user, and then you can just reprocess stuff later on. Another good example is you are having, let's say, purchase button. Purchase includes a lot of stuff like verifying user credit card, storing the user data, maybe sending it somewhere, processing at logistics center, and you don't need to do everything at the same time. You can just make a note that user wanted this purchase, and then you can just process credit card, you can process logistics, you can gather goods, everything you can do via publisher and subscriber. So let's say your application just publishes message, this user wants this item, and then it being spread over multiple processors that will just do everything further. So your processing can take days, but user will just immediately see the playing that, yes, we created your order, it will be processed and delivered to you. That's basically how internet shops are working. So let's go to the last point, which is much more of sysops or DevOps point, but you should also think about that. So you're providing some metrics as a developer, but these metrics should be gathered and processed. So do not hesitate to measure everything in your application if it doesn't waste that much resources, and it will help you in the future to go to production and find out what's going wrong. And or you should also, of course, provide logs, which should not be that verbose, not in development mode, but some logs should be clear and allow you to understand what's going on when DevOps are sending you the some problems from the production services which you usually don't have access to. So just consider that. Just think about that a lot, because this is the face of a modern software development. And also, if you're a DevOps or you are about to make some nice proposal to the DevOps, just think about monitoring-based alerts. One system that we're using is Alerta. So what it does, it gathers metrics. It doesn't gather. It consumes metrics from Prometheus, which gathers them, and creates alerts based on these metrics in the real time. So let's say you can have some monitoring system. You can have your mobile phone connected to this monitoring system, and something goes wrong on the software level, you would be immediately notified. So do not ignore this. You should think about that early from the beginning, and really be able to deliver some metrics on your application. Also, do not forget, if you're having a database or you're having this queue system that I mentioned before, they also have their metrics. It's also vital to measure them, because we're all people, we're all human beings, and we all make mistakes. So something can go wrong, not only in your code, but in vendor code. And that happened a lot. Also, I mentioned we're not humans. We are humans. We're not perfect, and of course, Kubernetes is also a piece of software. It also has bugs. It also has bugs by itself, and approach itself is not perfect as well. There is no perfect things in our world, so that's where we have some problems with the approach, which I would conclude one by one. So first of all, Kubernetes software is a software. It has bugs, as any software does. And one of the most prominent, which were discussed in the community, which caused a turmoil in the community, are security flows. So we had the run C vulnerability that allowed malicious user to run C code on the container and expose a root container to people that should not be in there, and also get access to Kubernetes network. And we had another bit worse, bit easier vulnerability is with API DDoS. So you could, as a read-only user to Kubernetes, DDoS API and also get access as a write user. So that's what should we deal with, and that's how we should upgrade Kubernetes every time something like that is being found. That's also a maintenance cost, right? Because you should track it. Also, Kubernetes, as I mentioned before, provides a network layer, but there is the networking itself is not a easy topic, and the way Kubernetes handle network is not perfect in my opinion. So it requires a really, really dedicated person, unless you just have one single net of pods and just one entry point. Everything other should be handled by a specialist, or at least consulted with a specialist that really working with that a lot. And of course, not you as a developer. Also, Kubernetes API has its own limits, because also Kubernetes stores some data, persists something. Usually it uses etcd, which is sort of a database for this, and this database is also having its own limits. So you should be careful, because we had our Kubernetes crashing when we deployed a lot of applications, and the traffic was so intense within the application network that our Kubernetes crashed on its own. So this Kubernetes is cool, fancy, shiny, but it's not perfect. Let's go to another point. So now, before, applications were just working on the bare metal stuff. You know that, right? So now it's working inside the Docker container, and Docker container connected to host system in case of virtual machine, because very often Kubernetes pods are being scaled on top of virtual machines to ease deployments and work for hosting providers. And of course, this is a huge buffer, huge proxy between your application doing system calls directly to the hardware. So this is one of my favorite pictures, which is quite accurately describes how it looks from the application perspective. So do not throw it out of mind. Keep it in mind always when you are dealing with Kubernetes. So the most efficient way, if you need the most efficient way, think about bare metal servers. And of course, every developer, I don't believe that there any developers existing in the world with more than 5 experience in IT field, in the web development field, that didn't do internal DDoS attack. But back in the days, computers were slow, servers were slow as well, and this DDoS attack could be reacted to within the human reaction time. Now it's not possible at all. So if you have a DDoS attack, it kicks off immediately. What DDoS attack is basically, imagine you have application 1 which sends some data to application 2 reprocesses some data and sends it elsewhere. But if you make an error in configs and accidentally pointing application 2 to application 1, it will send some postbacks to application 1. Application 1 would reprocess them, sends them to application 2, amplifying efficiently everything. And in some worst case scenario, you can have Kubernetes auto-scaling turned on, and then it will throw even more resources to this application, efficiently increasing packet storm, and that can lead to really, really bad consequences. So this is more of a human problem than Kubernetes problem, but just keep in mind and check everything on your application, especially configuration files. So these are sources that I use to prepare this presentation. Of course, Wikipedia always a great inspiration source, mostly for stealing pictures, but the rest was also quite nice to remind myself about history of the internet and how Docker works. So thank you for being with me today. I hope that was entertaining for you. Feel free to add yourself or knock at my LinkedIn page. I would be more than happy to discuss everything with you. If you feel that I'm speaking bullshit or I'm quite contradictory to myself, so feel free. I will be happy to welcome you on my page. Now I'm giving the word to Cedric.
All right. Thank you very much. It was very useful. We do have a couple of questions, and questions are keep coming. We do have couple of questions on Cassandra, so I would elude them or put them for later. So first question, and the first question is me actually. You show the workflow to design an app to go to Kubernetes, and you put Helm in the middle. You know, once the Docker image is ready, you put some Helm build, Helm deploy. And you know, what I'm doing is really, I do have my Docker image, then I move to Docker Compose to still work locally. And then I use some tools like Gcube or Compose with a K to change from Docker Compose to deployments. And it seems like having Helm is better. So what do you think?
Yeah, so this is a cool approach. Thank you, by the way, for mentioning Docker Compose, because I completely omitted that. Of course, running Kubernetes locally is a bad idea because this is very resource consuming and not needed. Docker Compose is easier. And yeah, so when you're creating a configuration, you can use Compose, which would just transfer this to Kubernetes appropriate format. But the thing with Helm is that it manages a deployment itself, right? So Kubernetes on its own is not designed with a very complex logic. So if you're applying a new release, you should do this manually. You should tell Kubernetes which container where should be put, when it should be put, with which strategy should it be rolled out one by one, and should be just all containers deleted and restarted, right? So it's quite cumbersome. It's easy when you're having one cluster or just one application, but if you're managing a lot of them, right? Like we are managing 60 or 100. It's better to have some tool which would decide it for you and which will allow you to extend this infrastructure as a code approach to deployment. That's why we're using Helm. It's actually this sort of de facto standard in the industry because it allows you to easily scale up a lot of deployments and create new ones with just a simple configuration files.
Okay.
I would recommend my colleagues from KubeCon that were observing Kubernetes, which were observing Helm chart features. It's really hard to explain the Helm charts itself, but definitely this is a way to go when you're having huge deployments.
Okay. The question is second question is also about Helm and is okay on Helm chart standard image are available. How do we do our own custom image? What is needed?
I need to refine the question a little bit, right? Helm chart is the thing that just contains Docker image, and Docker images can be standard or can be prepared by you. So when you're preparing your Docker image, you should find some repository service. If you're using Google Cloud, they have their own. If you're using your own, feel free. You can use Artifactory from JFrog, or you can use some of, let's say, Nexus, because it's a free. You set it up on a separate server, which Kubernetes has access to, and then you just put the links to the Helm chart. Easy as that. So when Helm has access to this server, it will just fetch the image and put this to Kubernetes. Put the information about it to Kubernetes. I hope that answered the question. That's how I understood it.
Yeah, I think pretty convenient. Yeah, this is what I would do. I do have a question about stickiness. So have you ever had to use some stickiness in your code? You talk about stateless, of course that would be the best, but sometimes app needs to talk to dedicated shard or anything. Have you tried something like that?
So I did try dedicated sharding. Like I understand what the question is. So like something like Google does, right? When one application is able to access only, let's say, A shard, where all information starting from A is stored, and then B shard and so on. So yes, this is also state. But this state is not stored in a memory per se, right? So you can have, of course, some state. You can have some configuration, but please make sure that this configuration is either can be easily recovered. So you have some stateful database which also stores the state of each application, where application can know about its state. Something like etcd or Zookeeper. So let's say your application is working like Google. You're doing a search. You have A, B, C, D, E, F, G, and so on. And each application you're starting is working with some specific letter. Let's say your D application crashed. Then new application instance started. It should go not to the it should not figure out anything by its own. It should go to Zookeeper and know, okay, Zookeeper, which 3 letters you have for me, which shards I should access. I can access D shard. Okay, I will be the D application. That's usually how it's being done. So this, what I know about stickiness. Also, on our own experience, we even having shared state between applications. So we are having shared cache. But I would also mention that shared cache, if one application crashes, it's not a big deal. This cache can be easily recovered. It's not the stuff that's easy to lose. So that's just it.
Yeah, so I agree. And so question keep coming about stateful. I think it's a trickiest party in Kubernetes. So
but I also
sorry.
I also can see that people would demand probably Helm charts and stateful presentations in the future.
Oh yeah.
Think about that.
Yeah, that would be cool to have you, of course. So suppose we deployed our stateful application on Kubernetes. What to do if a node goes down?
Yeah, that's a tricky question. Yes, so it depends. Let's say your stateful application is a database crafted by you. you don't love Cassandra or Postgres or whatever tool we're having on the market, you decided to go with your own database. So please make sure you made it high available. Usually how it's being done, I will give an example of Postgres, and also I will talk about Cassandra from Cedric Permission. So
Please.
How Postgres is doing that, it has one master, because Postgres is naturally limited by having only one master that stores the data, and has another node marked as slave, which is usually hosted on even another server. That makes a lot of sense, right? Another node.
Mm-hmm.
So one node which contains master is just accepting writes and reads, and then duplicates the data over to a slave. And if a slave node goes down, not a big deal. On the new node, it which will be restarted, you have empty database which will be slowly recovered. And if master goes down, slave tries to understand what needs to happen, and then it just takes over master role. It's of course backed up with a lot of service meshes, so you should also have to have something on the network layer which will understand who is master now. But generally, this is the approach. And please, if you're doing your database, please ensure that you at least have master-slave replication. And when you're deploying this, make sure that first of all you're using Kubernetes stateful sets, which will ensure that it cannot be that easily restarted and lose mounted volumes, and also make sure that you spread it over multiple nodes with special tool called taints and anti-affinity. And of course, Cassandra is much better in that sense because it allows master-master replica, so you can have two nodes acting as a master with some special rules for logical split, and they would be consistent and up to date. And if one of the masters goes down, another immediately takes over, which causes the downtime, because of course, if Postgres master is down, there would be some downtime for your users, which hopefully not that big and self-recovering. Yeah, so this is how you have to deal with the stateful applications. If you cannot do application stateless, just make sure you have a lot of instances of stateful applications and they're consistent between each other.
All right, thank you very much. Good deep dive answer as well, I guess. So see some questions. So first, any documentation about Docker image and Nexus repository? Maybe I will take this one very quickly. So in this channel, we had the 4-week series on Kubernetes, Docker and Kubernetes. And there we explain you how to build a Docker file and how to build an image, push an image to a Docker registry. And so you can use the Docker Hub, which is a public one, or create your own, just to reduce the bandwidth needed each time you push a new image. It's not like really Nexus repository where you would store Maven artifact, but it's on the channel really. Docker build, Docker login, Docker push. Those are explained in the previous video.
Yes, I would definitely say that I would recommend this course. I looked at with a lot of fun. I really like this course. That's very good explained. And also you can visit hubdocker.com and take a look at the vast amount of applications there. Thank you, Cedric, for announcing that.
Oh, sure. So next question is, I don't know, let's see. So Bernard asked that actually has some conflict between Symantec antivirus and the OpenShift cluster. So did you experience some troubleshooting with antivirus and Kubernetes?
So actually, as you can see, obviously I'm running Mac. I'm desperate user. I don't have any antivirus, but I managed to set up a Kubernetes environment on Windows, on even Windows 10, which is basically a user system.
Yeah, without the Pro version, it's pretty tricky, right?
Yeah. It is very tricky. I just was paid for that. Otherwise, I wouldn't touch that.
Hypervisor and all that stuff. Yeah, I know what it is.
Yes. So actually, yes, antivirus blocks Kubernetes as potentially vulnerable vulnerable process because Kubernetes works also in a virtual machine sometimes, and is opening a lot of ports for its own. Actually, as far as I remember, for Symantec, there is an official patch, official library extension, which allows antivirus to work with the Docker environment and Kubernetes. But my advice here is, if you are running Windows and you want to set up a Kubernetes, which is quite hard on its own, I would definitely recommend not using antivirus software. That's really hard. Sorry if I couldn't help that much in here, but
no, that's already a good thing to know. That
not...
seems like a patch exists, and true. So we are doing some teaching with Kubernetes, Docker on Linux, Windows, and macOS, and Windows is always tricky. We must provide some dedicated cloud environment most of the time. Windows is conflicting with Docker when we want to go deep dive, using Kind or Minikube or any Kubernetes local stuff make Windows not really happy.
Yeah, so I would really recommend using Linux because in my opinion, setting up these Windows is very glorious deed. But if you want to learn on Kubernetes, it's not maybe the best choice.
Yeah, so maybe this question is for you, and I will take 2 more questions and close at 3 p.m. let's say my time, so in 5 minutes. So next question would be, is it advisable to use vanilla Kubernetes in production? I think against probably cloud provided Kubernetes like GKE, AKS stuff, or even OpenShift. Would you deploy your own K-test cluster, and which version would you use?
That's a very good question. I mean, all the questions were very good and make me sweat a little, but this question is very good in the sense that I was stuck with the same one 2 years ago. We were choosing over Google Cloud provisioning services or deploying vanilla Kubernetes to, let's say, Amazon Web Services, because Amazon doesn't have anything on its own. So my answer here after 5 months of trying is, if you don't have a special dedicated team at least of 2 people knowing what they're doing, I wouldn't go there, because vanilla Kubernetes is easy to install but really hard to configure. So you can really easily install kubelet volumes, you can really easily install the master node, but to make it production ready, you need a huge way of trials and error. Even though we now have very nice configurations ready for Kubernetes, it's still not worth the effort. I would, in worst case scenario, I would take OpenShift, or I would go for Google Cloud Engine, because highly likely if you're working in a medium-sized company, you are probably just required to move your infrastructure there. And if you're working in a big company, you probably have a dedicated team, and then that's where they would decide this. So I'm a lazy person.
That's a good quality as a developer.
Definitely.
Maybe one last question is how to secure a Kubernetes cluster. Is there a way to configure SSL for Kubernetes like Cassandra? So when it comes to Cassandra, of course, you can set up SSL communication in between nodes, and for client app to connect. You won't have the same settings if the app is running inside the kube cluster and can resolve the service names, or outside, and now you need to open port and use some ingress or SNI tricks to make that work. Of course, you can make kube secure and open port only on TLS SSL with the proper ingress configurations.
Also, I would mention about security. There is a concept inside Kubernetes which not every developer or even every sysop knows about, is secret keys. So if you want to connect to database but you don't want to share keys with developers or expose it anywhere, you can use a secret container, secret storage within the Kubernetes, which would provide the keys only when they are needed. very good concept. I would highly recommend that.
All right. Well, thank you very much. We are at the top of the hour. So thank you very much for being with us. I guess you pick a couple of subjects you want to go more deep dive. You will have
Yes, definitely.
some documentation to read. You're always welcome. If you want to come back, please tell us. We would be very happy to host you again and share more love around those technologies. And with that, see you next time. We will redo the same session in a couple of hours for people living in America and such. But until now, see you next time. Bye.
See ya. Bye.